We will start this lecture with a thought process from T.S. Eliot, English poet, who says that only those who will risk going too far can possibly find out how far one can go. And let us recall as usual what we had learned in the last lecture. We are basically looking at the cycle analysis, ideal cycle analysis. We have already covered the turbojet engines, and the last lecture we discussed about the turbofan engines, right. We derived the relationship for thrust specific thrust, thrust specific fuel consumptions, and various efficiencies, and then we carried out a parametric analysis to look at really how these performance parameters behave with the various parameters. What are those parameters we looked at? Those parameters are pressure ratio across the compressor, pressure ratio across the fan, bypass ratio, right, and of course the altitude and other things one can think of. So, if you look at it, you will find that bypass ratio and fan pressure ratio plays a very important role for affecting the overall performance. In modern days, you might be knowing that turbofan engines are being used for a large aircraft, and whenever you talk about large aircraft, we need to provide the higher thrust, and on the other hand we will have to reduce the fuel consumption or lower TSFC. And we have looked at conventional turbofan engine where there are two stream, one is fan stream and other is what you call the core stream, right. And overall pressure ratio is goes on increasing to enhance the thrust, right. But whenever it increases, then what happens? It will be having a problem with the instability in the combustion chamber, because the pressure ratio across the compressor increases, right. As it increases, then there will be problem of surging, right. Generally, of course, some of you might be thinking, oh, pressure surging can occur in the low pressure, right. It is generally not likely to occur, but however, of course, when you will study about this problem of surging in a compressor particularly, then you will appreciate that it will be occurring at higher pressure. Whenever the pressure ratio across the compressor increases beyond certain limit, then it will subject to surging. If surging will occur, then it is a problem. Now, how to overcome that problem of surging, which will cause the instability in the whole engine, right, is a very, very important aspect. And also you want to make it more compact, otherwise your efficiency, your performance parameters will be affected by the effect of surging or by the onset of surging, right. So, therefore, various configurations have been developed over the years. I will show you some of them, and the important one is what you call configuration is the single spool engine, right. Single spool means what? Is basically single shaft, the shaft which will be connected to both the low pressure compressor and low pressure turbine, low pressure compressor, high pressure turbine, and all the things, low pressure compressor, high pressure compressor, then high pressure turbine and low pressure turbine, and two spool engine where you are having two shaft which will take care of surging, and boosted two spool engines and three spool engines. Of course, there is another varieties which have come up is the geared fan, right. There is another configuration which have also come up, and it is not from the problem, not from the perspective of avoiding the surging, but however to compactness, mixed fan engines, right. What we have done, the separate fan, like means mixed flow engines, like fan flow and the core flow is separately being expanded in two different nozzles, but there is a turbofan engine where you can mix together and then expand it in a nozzle such that the noise level can be reduced, right. Of course, you can get the thrust and those things I am not going to discuss. What I am now concentrating on discussing about the engines. If you look at the single spool engines, basically it is a very simple one and it is being used in a like a fighter aircraft and other places, but however some of the modern fighter aircraft also uses two spool engines. But if you look at the SNECMA and other series they are having, let us discuss about two spool kind of engine. If you look at here, the high pressure turbine, this is basically a turbine, right. High pressure, HP stands for high pressure, it will be running the high pressure compressor, right, and the low pressure turbine will be connected to the fan, because the fan cannot operate at a higher RPM. Why? Because the tip particularly will be have a high speed and it may exceed the speed of sound. If it will exceed, then the shock will be formed, and these are not designed for that. Therefore, the losses will be very, very high, right. These are all subsonic turbo machinery what is being used as of now. In future, maybe transonic or supersonic will be used. I mean, maybe used. Maybe some of you will be involved in designing that, which is a very, very challenging job. So, but this kind of engines is being used, and particularly I have taken an example. This is a G engine CFE 738, and which is quite compact and is being used, but it is having limitation because the RPM will be what you call deciding that how much air will be entering into, and also the number of stages what one can have, particularly in turbine. And so also in the compressor, if the RPM is very, very constant or maybe very high, then naturally you cannot go for more number of stages, right, because the pressure will be, and you cannot go for a high pressure, then naturally you will have to go for a more number of stages, then it will be compressor will be not operating properly, particularly last stages of the compressor will be subjected to the surging due to the adverse pressure gradient, right, which will be and there. So, in order to overcome this problem, people thought about using the boosted two spool, because there is a limitation of the pressure ratio what one can achieve in a compressor in case of two spool engine. Now, but whereas my requirement is higher pressure ratio without surging problem. So, naturally I will have to go for boosted like kind of thing. What they have thought idea is that why not have a compressor which is attached to a fan which will be rotating, this is the shaft, the low pressure turbine is connected to that, and you can get some kind of a pressure, more pressure ratio as compared to two spool engine. Of course, they are successful, but when you go beyond certain limit you cannot really avoid the surging problem. So, therefore, there is a need to go for the three spool engines, and there are several engines people have designed. This is quite a popular one in few years back, but today the three spool engine is being used very rampantly, like CF6 and GE9. GE means basically General Electric, and CF also is General Electric. Earlier days they used to have, but today they are more systematized the nomenclature of the engine, and PW is your Pratt & Whitney 4000, which is being used in your Boeing like in your big aircraft kind of engine. So, three spool engines where you can have high pressure turbine is running the high pressure compressor, there is intermediate pressure, right, okay. Intermediate pressure turbine will be running the basically low pressure compressor, right, and the low pressure turbine will be running the fan. This is basically a fan, right. and here it is you can have a more range and you can go for a higher pressure without really encountering the problem of surging. So, therefore, this is being used, and of course, you can get varieties of engine like Rolls Royce, like they use this thing 211 and 199 engine. There can be several engines, I have taken few of them example, but there is another engine which is quite what you call being promoted by the Pratt and Whitney, 2 spool geared engines. Instead of using a what you call to connect this low pressure turbine with the fan, they have used a gearbox, but keep in mind that design of a gearbox is not that easy because the power level will be quite high, right. And we will see this kind of problem particularly in turboprop engine, but here the power from the low pressure turbine which will be transferred to fan will be relatively low as compared to the turboprop engines, right. So, therefore, they are designing this gearbox which is quite will be noise, like it makes a lot of mechanical stuff. So, you can reduce control this speed and you can manage to have a higher efficient fan over a whole range of operation. So, therefore, this is they are already using this advanced fan and advanced technology fan integrator engines, but it is not being very much popular as of now even today. So, now what we will do, we will take up an example of how to solve a problem like an ideal turbofan engine flying an altitude of 10 kilometer, flight Mach number of 0.85. The pressure ratio across the compressor and fan is 10 and 2 respectively. If you look at the total compression ratio in the core stream will be 20, 10 into the fan pressure ratio is the 20, keep that in mind. Bypass ratio of turbofan is 5 in this example. You will have to determine the specific thrust, specific fuel consumption, propulsive efficiency, thermal efficiency, overall efficiency, and we can determine the static stress and TSFC under the static condition at the sea level. So, these are the data are given as I discussed. So, first we will have to find out what is the flight velocity. We can get that very easily because we know this altitude, from this altitude we will get this temperature, and then V naught is equal to root over gamma r T naught into multiplied by the flight Mach number. When you substitute these values, you will get 254.6 meter per second. And as I am emphasizing that whenever you want to solve a problem, it is better to solve in a systematic way, not going into the formulas, right. But whenever you are going to do a parametric studies, it is advisable to use those formulas so that you can write a program and do it very easily, repetitive jobs, you need not to waste your time. But to appreciate the how whatever these things, it is important to solve this problem. So, what are the happening, I have already talked about that thing in the TS diagram. So, this is basically compression, 0 to T2 is your fan and T2 to T3 is your compressor, and T3 to T4 is basically combustion. This is the combustion, right, and expansion is 4 to 9. In this case, this is a turbine, low pressure turbine, high pressure turbine, and then the nozzle. This is the nozzle portion, right. And similarly, in the fan stream, this is your fan stream, like it is going from P naught to the PT2 and then PT2 by PT3, 13, right. And of course, again expanded because ideal, so it will be coming back to the P19, which is same as the P naught. So, from compressible flow relation or isentropic flow relation, we can get Tt naught divided by T naught is equal to 1 plus gamma minus 1 divided by 2 m naught square. We can substitute these values, we will get the total temperature Tt naught is 255.6. Keep in mind that is not very different than 2 to 3 because the Mach number is being very small, and we know that Tt naught is equal to Tt1 is equal to Tt2, right, because it is an adiabatic process. So, again from isentropic you can get the pressure ratio, right, because what we are doing, we are going on each point and then getting this thing. Sometimes you may avoid, you know, doing this in a systematic manner. I know, like whenever you will be in exam, you will take a little shortcut route, but you may commit an error in the process. One has to be careful. The PT naught is equal to 42.5 kilopascals. So, for the fan stream, we get actually TT2 is equal to 256.6 Kelvin and PT2 is equal, same as the PT naught 42.5 Kelvin. That means we are looking at fan streams, right, and by the same way we can look at the compression, you know, in the compressor how much change in the temperature is occurring. So, if you look at the pressure ratio across the fan, phi f becomes PT3 by PT2, which is given, 2 is given. So, you can get PT3 is 0.8 85 kilopascals, and we can estimate the temperature by using the isentropic relationship, and which is basically it is given, like this is nothing but your pi f, this portion, you know. So, therefore, you just substitute these values and get that, and you know TT2, so you can get 311.64 Kelvin. So, there is a very less, you know, change in the temperature, and as we know that P19 is equal to P9 is equal to P19 is equal to P0, right. That is for an ideal cycle. For real cycle it need not to be, right. So, V9 tin square we can get 2 Cp T19 minus T9, we can take it out and you can express in terms of pressure ratio. So, these already we know, right, P9 we know is nothing but your P0 and P19 we know. So, we can put substitute these values, and when you will do you will get V19 is 421.4 meter per second, right. So, if you look at, there is an increase in the velocity due to the work addition to the flow by the fan, right. So, overall pressure ratio across the both compressor and fan or due to compression in the core engine, right, is pi c is 20 as I told. So, you can get TT3 is equal to TT2 pi c gamma minus 1 divided by gamma, this for isentropic relationship, you can get this 602.1, and similarly you can get PT3, right, because you know the pressure ratio. So, you know the PT2, so you can get that very easily. By energy balance across the combustor, we can estimate fuel air ratio F, which is we have done for the turbojet engine is similar to that, just to substitute these values because it is given here 1400 Kelvin TT3. So, TT2 you know you can get these values. By carrying out power balance between the compression turbine and also the fan, right, is not it, fan, we can estimate temperature. For example, we know that WC plus W fan is equal to W turbine. If I take this and use that first law of thermodynamics for this, then you know I can get this an expression, and we are using the same Cp, but in keep in mind in real cycle we will be using different Cp. So, in this case the Cp is cancel it out, you will get Tt5 is equal to Tt4 minus T3 minus T2 minus alpha T13 minus T2. So, this alpha comes into picture because of mass, you know, being separated. This is nothing but your bypass ratio. So, when you substitute, because alpha is known, T13 is known, Tt is, this is also known, this is known. So, T4 is known, that is your 1400, right. So, you can get Tt5. If you look at the you know in the turbine, it is expanded from 1400 to 773.3 Kelvin, you know, temperature. By using this isentropic relation, we can estimate total pressure at the exit of turbine. The PT5 is equal to PT4. we know this Tt5, we know Tt4, substitute these values, you will get the pressure at point, at this point 106.46 kilopascal, right. So, which is a very systematic way it is done, there is nothing really to understand because it is quite easy. To estimate the nozzle exit velocity, we will have to assume of course Tt9 that is equal to Tt5. It is not we are assuming, it is because it is adiabatic process, right, and under an ideal condition, right, there is no losses. So, Pt9 is equal to Pt5. So, when you substitute this value V9 is equal to root over 2 Cp Tt9 minus T9, and we know this pressure ratio which can be expressed 2 Cp 1 minus P9 Pt by power to the these gamma ratios, gamma minus 1 divided by gamma, and when you substitute these values you will get V9 is 714 meter per second, and Ts we can estimate very easily, right, because we know V9 and alpha is known, V19 already we have found out, and this V0 is known, this is known. So, you substitute you will get the specific thrust what it would be, that is basically 1293.4 Newton second per kg. So, TSFC can be estimated because we have already estimated F, right, divided by specific thrust. So, you will get 1.44 10 power to minus 4 kg per Newton second. So, we will estimate this propulsive efficiency, thermal efficiency and overall efficiency. If you look at this we have already derived, we will just use that, or we can use from your own thing, that is the thrust power, total thrust into the velocity, this portion divided by the, you can use that. So, V9 is known, V0 is known, alpha is known, V19 is known. So, you can estimate this and substitute those values and get that. What I would suggest that although I have used here the derived relationship for propulsive thermal efficiency, but you need not, you can go to the basic definition and then do that, so that you need not to memorize it. So, you will get that propulsive is 65.32, and similarly when you substitute these values of thermal efficiencies for all velocities like V0, V9 and V19 and alpha is the bypass ratio and the heat of combustion. So, you will get 63.03 percentage, and the overall efficiency when you just multiplied both you will get it is 41.19. If you look at the overall efficiency, if you compare of course the same conditions, you will find that turbo fan engine is having higher overall efficiency than the turbojet or the engine kind of thing, right. So, you must appreciate that point, and particularly I will be giving some problem in the assignment where you could get a chance to feel for it by solving yourself. So, now we will move into the turboprop engine, and which is basically being used whenever we want to have a higher thrust level kind of things, right. And of course, it will be what you call whenever we need to have also the TSFC kind of thing. So, the typical turboprop engine is being used, being shown here the schematic diagram, that is it is having a propeller, right. Instead of a fan, it is a propeller which is unducted, there is no duct, and keep in mind that the length of the blade in a propeller is much longer as compared to the length of the blade in a turbofan engine or the fan. There is a two difference, one is it is the unducted fan you can say, but not only that, but its also length of the blade is higher. So, therefore, it has to be operated at a very low RPM. Why? The same reason that if the length is higher, then at the tip the velocity or the local velocity there fluid will be much higher, right. Okay. Is it clear? Omega into R. So, if you look at that is the very higher values, and therefore, it has to be rotated at a lower RPM. And therefore, the gearbox is being used to reduce this RPM, and this of course, the shaft if you look at it can be very clearly seen, it is a 2 spool kind of engine, where the low pressure turbine, this is your low pressure turbine or the low pressure turbine, right, low pressure turbine is being connected through a gearbox to the fan. Of course, the high pressure turbine is being connected to the compression, and this is your combustion chamber, and the station number we are using is the similar one. Now, let us look at the process what is happening. It is 0 to 2 is your compression, and there will be some compression, right, due to the propeller, and keep in mind this is your core engine, this is your core engine, air is also flowing, this is your core engine, right, and this is the propeller air will be coming over here and going out, right. And there is a compression in the what you call in the compression, and there is a heat addition, constant pressure heat addition, combustion, and there is a high pressure turbine from 4 to the 4.5. There is the expansion in the turbine high pressure and expansion in the low pressure turbine, that is 4.5 to 4, and this is your nozzle, low pressure turbine, and this is high pressure turbine, HPT and LPT I am telling. Okay. So, we need to carry out this analysis. Keep in mind that we do not know how much air is passing through the propeller, because it is unducted. So, how to handle? Can we go by that? That is a one concept which is very important, right. And another one is that the amount of the power given to the propeller is not being converted into the kinetic energy, because always there will be slip, right. So, therefore, we will be using a efficiency known as propeller efficiency, right, in this analysis, and we are assuming the gearbox efficiency is 1, which is not the case. That will be we are using ideal cases, the gearbox efficiency is equal to 1, right. So, the total thrust produced by an ideal turboprop engine can be contributed by what? Two things. One is your core engine, right, in the core it is going, and another is due to the propeller. So, if you look at which is the major portion in a turboprop engine, is it the propeller will give you more or the core engine will give more? Generally, propeller will give you the more thrust as compared to the provided by the core engine, because the expansion in the nozzle will be very small, although it is not being reflected in a TS diagram. Please keep that in mind. Okay. The dimensionless work output coefficient C we can define as the C is the power produced per unit mass of flow rate through the core engine. This is a very important one, you must understand this, because why you are using the amount of mass passing through the core engine, because we do not know really how much it is going through that, right. Okay. Because the openly it is going and how much it is contributing the thrust. So, therefore, we use this work output coefficient instead of now we will be operating both thrust and the work output coefficient, trying to connect it, convert, I am like connect both the things, where all the other analysis we are using thrust, we are not bothered about what is the work output kind of things, because we are interested in thrust there, and there is no problem of handling that. So, there is a little difference in analysis, please keep that in mind. So, therefore, for the core stream and propeller, right, work output coefficient can be expressed as Cc, this is your thrust produced by the core engine, that is tau Ts Tc, and then V naught is your flight velocity, right, divided by m naught Cp T naught. It means this is with respect to total energy, right, which is coming m naught Cp and T naught, right. Cp T naught is enthalpy into mass, enthalpy, this is per kg, and then this will be 2. So, similarly prop, the work coefficient for the propeller will be eta propeller, that is the propeller efficiency, right. This is basically propeller efficiency, and the work input to the propeller divided by m naught C Cp T naught, right. Keep in mind that we are not using total mass, we are using all the time m dot C, right. So, it is having implication when we interpret the data, because that is why I am emphasizing this point. Okay. The total work output coefficient will be C total is equal to C propeller, right, work output coefficient plus core engine, right, Cc. And from the definition of the work output coefficient, we can rewrite expression for total thrust. What is the definition? We have already seen, that is the thrust, right, total thrust into the flight velocity, right. So, total thrust will be basically the propeller thrust plus the core thrust is equal to C total into m naught total, right, Cp and T naught divided by V naught, that will give me the total, right. So, expression for the thrust developed by the core engine flow rate will be can be expressed in this way by using the similar analysis or the same analysis rather for the turbojet engine, right. So, Ts is equal to T by m naught is nothing but A naught V9 by A naught minus m naught, right. And then in place of this V9 by A naught minus m naught, you can write down this bigger expression which we have already derived for the turbojet engines, right. And keep in mind that this is all these parameters are there like tau lambda, tau c, tau r and tau t, right. So, these are basically temperature ratios across the components like your turbine, compressor, air intake, and lambda of course is little different thing which I had defined earlier. So, the work output coefficient for the core engine we can say that Tc by V naught divided by m naught Cp T naught, and we can express this in terms of like V9 and A naught, because we have already we can put these thing values here and over here and get that, and you will find that little analysis if you do, you will find out this gamma minus 1 m naught in the bracket V9 by A naught minus m naught, you will get these values, right. So, and if you look at what we are using, we are basically expressing Cp in terms of gamma. So, the specific power of an important parameter for turbojet engine which can be derived like Sp, that is the specific power, is W dot total divided by m naught h naught, which is nothing but C total, Cp and T naught, right, and where T total is equal to C propeller plus Cc, right, because if you look at this, you will have to go to the definition of the C total and then you will get that this is nothing but T total Cp T naught. So, in order to find an expression for Cp, let us strike a power balance across the high pressure turbine and propeller. So, if you look at this is propeller work input is equal to m dot 4.5, this is nothing but your what you call m dot c, isn't it, because this is the core engine which is going, whatever the air is going through that core Cp, and Tt 4.5 minus Tt 5. So, by definition we know that C propeller will be basically W dot propeller into m dot Cp into T naught, and a W dot propeller we have already seen that it is nothing but your in terms of propeller efficiency and temperature, and if you just rewrite you will get T lambda tau T H. This is basically tau T for the high pressure turbine and tau T L is for high pressure low pressure turbine. Similar to other engines, the expression for fuel air ratio you can get the similar expressions which we have already derived for the turbofan and turbojet engines even, right. So, and TSFC you can get in the similar way m dot F divided by T is equal to F into the T divided by m dot C. Keep in mind what we are doing, we are basically looking at even the mass flow rate through the core engine, right. The power specific fuel consumption expression, because it is a turboprop engine, therefore, we are interested in the PSFC or the power specific fuel consumption. So, that is m dot F divided by W dot total. You know this F and C total Cp and T naught. So, if you look at, you substitute these values, you will get that. And the expression for the thermal efficiency will be similar to that the turbojet engine, and overall efficiency it is more important that you first really find out the overall efficiency in case of turboprop engine, right. But in case of turbojet and turbofan engine, you find out first the propulsive efficiency before you really find out overall efficiency, right. But it is other way around, because we need to find out this and then you will get, because we do not know really how much it is going. So, and this is the expression the similar way, I mean like same coefficient, but this is the by definition m W dot total divided by m dot F delta S C, right. How much work being put into the engine, how much work being produced by the engine, and then how much fuel being burned, right. So, by knowing this overall efficiency and thermal efficiency, we can get the propulsive efficiency, right. This is, keep in mind, this is not propeller efficiency, this is propulsive efficiency which is due to the motion of the vehicle or the engine, right. So, that you should keep in mind. So, now what we will do, we will carry out a parametric analysis as we had done earlier, and then we will see what we are getting. And here what we are doing, we are basically taking the 3 tau t values. Tau t is equal to 0.6, 0.7 and 0.8, and we are varying the pi c from 0 to 40, you can say, kind of things, and then we are plotting it specific thrust versus the pi c for a certain altitude, and certain flight Mach number kind of things, right. You will find that this, when tau is 0.6, what is the meaning of that, and when tau increases to 0.8, what is the meaning of that? Tau, that means temperature ratio across the turbine, right, tau T, isn't it? This is tau T, right, that is your temperature ratio across the turbine. Lower means it is what? Less work, it is more work extraction, because the temperature at the exit of the turbine divided by the inlet, right. So, if it is a smaller value, that means it is being expanded well as compared to the bigger values, right. Are you getting my point? For example, this is your basically 4, right, 4, and let us say this is your 5, this is your turbine, right. That means this tau is T is equal to TT4, TT5 divided by TT4, that means 5 is smaller, that means more expansion, right. as compared to the when the tau t is larger. That means smaller means more expansion, larger means less expansion, right. So, keeping that in mind, that if you look at this line is basically, this is your tau t 0.6, and you will get that specific thrust increases and then it decreases with the pi c. And as you go to the 0.7, and this is your 0.8, and which is obvious that it will be decreasing, and it is also, if you look at peak values are also decreasing. That means peak values is basically increasing point with the what you call larger expansion, that means tau t being smaller, and it is occurring at a higher pressure ratio if you look at, right, because if the expansion is more, you need to provide the more compression ratio, pressure ratio. And of course, if you see this, this is your 0.8 and this is your 0.7, and this is nothing but your TSFC, thrust specific fuel consumptions, and this is your 0.6, and you will see that minimum values are also minimum decreasing, and so also the overall like TSFC decreases. That means if I go for what you call more expansion, then I am having a what you call the lower TSFC values, and also it is coinciding. If you look at minimum values here, it is almost closer to that in comparison to the turbojet and other engines. So, that is a good part of it. That means TSFC and the minimum TSFC and the peak specific thrust are almost closer. You can say that you can operate well, and which is better as compared to, and keep in mind that here the specific thrust is much higher as compared to the turbojet engine. If you look at the numbers, here something 1800 kind of thing for tau t 0.6. Is it right something, or is it wrong? Huh? What is that? It is right, because you have divided this specific thrust with respect to the core mass flow rate. That means mass flow rate is very, very small, but in case of turboprop engines, right, if you look at, if I take total mass flow rate, then naturally it will be smaller. Are you getting point? The specific thrust always smaller for turboprop engine as compared to the turbojet engine, but here it is an artifact because the assumption or the way we have analyzed, that you keep in mind. Okay, it is a very important point. You may not observe that thing, right. So, the propulsive efficiency and overall efficiency I have told, this is basically the thermal efficiency, this line which increases pi c, because it is the same as that of your turbojet engine, but however the what you call, this is 0.5, that is your what you call the propulsive efficiencies, and this is 0.8, and whereas the overall efficiency, if you look at, it is increases and then it decreases, it is having some peak values here, and similarly as you goes on decreasing this increasing this tau, it gets reduced. That means the more expansion in the turbine, right, the better is the overall efficiency. That is one point, and the other point is that its peak values at which the peak overall efficiency occurs at a higher pressure ratio across the compressor. That means my compressor will be more bulky, because number of stages will be higher. So, then you need to look at these aspects while designing a turboprop engines. Of course, several other analysis one can carry out, but I will not consider those things. And let us look at an example. A turboprop engine is flying at an altitude 7 kilometers, that is T naught 242 Kelvin and P naught 41, and flight Mach number of 0.5, in the gas generator 50 kg of air is compressed with the pressure ratio of 12. The exit temperature at the combustor is 1400 Kelvin, temperature ratio across the turbine is 0.5 we are using, and determine the thrust developed by core engine and propeller and TSFC if the propeller efficiency is 0.9, and as usual we can find out the flight velocity, I mean because Mach number is given, right, and we know this temperature T naught is the, and we know this gas constant, specific gas constant, we substitute, which happens to be very very low, 155.9 meter per second, right. And propeller thrust by the what you call propeller thrust can be expressed C propeller m dot C Cp T naught by V naught, and we can find it is given the propeller efficiency W dot P propeller we need to calculate, and V naught already we have calculated. So, and we know that m W dot propeller is nothing but m dot C Cp Tt 4.5 minus T5. And when we carry out this Cp and then energy balance across the low pressure turbine and propeller, right. So, we will get we carry out energy balance across the low pressure turbine and the compression, this is not low pressure, this is basically high pressure turbine across the compressor, because this is your compressor, this is your basically high pressure turbine, right, isn't it. So, I know this Tt4 is given and I need to find out this Tt3, right, and pressure ratio is given. So, I can find out the similar way Tt2 has to be found out, and of course, this Cp will cancel it out. So, I can get Tt 4.5 is equal to Tt 4 minus Tt 4 minus Tt 2. So, we need to determine basically Tt 3 and right and Tt 2. Tt 2 is basically Tt 2 divided by T naught into T naught, and this already we know. So, we know these values, we know these values, we know gamma, we can determine what will be Tt 2. Similar way what we had done. And the values of T3 can be easily estimated because we know the pressure ratio across the compressor, right. So, we can find out that values very easily because we know this is 12 and the gamma we know 1.4 we will be using, and we can get these values. So, by knowing these values of Tt3 and Tt2 and Tt4, so we can get Tt 4.5, right. And the thrust propeller we can get as T like eta propeller into m dot C. M dot C is given to you, like how much air is passing, that is 50 kg per second, right, which is important parameter, and Cp is known, and Tt 4.5 minus Tt 5, right, and V naught you can get this how much it is having, right. So, because how we will get this Tt 5, tau is given, right, tau t is given. So, tau t is what, is it 0.5, right. So, that is nothing but your Tt 5 divided by Tt 4. So, from that I can get, because the Tt 4 is your 1400 into 0.5, Tt 5 is equal to 700, right. So, that is given. So, you can find out very easily. So, the thrust produced by core engine will be Tc is equal to m naught V9 minus V naught. So, the nozzle velocity, nozzle exit velocity you can get by this expression, and we know this Tt5, we know Cp, and it is nozzle is fully expanded. So, we need to know the total pressure ratio, pressure ratio across the nozzle, that is Pt5 by P9, right. So, this you can do that and you can substitute and get that it is happens to be 0.8. If you look at PT9 by P9 is equal to P9 by P0, which is nothing but your 1, P0 by PT2, PT3 by PT3, PT2 by PT3, this is nothing but your pi c, it is given, PT3 by PT4, this is nothing but your what you call 1, and PT4 by PT5, and tau t is given. So, you can substitute those things and get that values, right. Tau t can be expressed in terms of your pressure ratio, right, or the pressure ratio across the turbine can be expressed in terms of tau t. So, substituting all values we will get V9 is these values 294.94 meter per second, and after knowing this thing we can get basically the Tc, because sorry there will be this will be Mc and V9 minus V0, and we know these values we can get Tc, and by knowing Tc we can get what will be the total thrust, because the thrust will equal to propulsive thrust, right, or propeller thrust, sorry, propeller thrust plus the core engine thrust will give you the total thrust. You can see that the propeller thrust is much higher as compared to the core thrust, is a very small, right. Okay, this is quite small, this is large. So, let us evaluate the amount of fuel consumption by striking this valence, right. This will be m dot c basically, and if you look at, you substitute these values, because this is known, and this is known, and this is given, and this is also given. So, you can substitute and get those values. So, TSFC you can get m dot f divided by T. So, you can get those values. So, then we need to find out the overall efficiency, because you know this T, the total, this is basically total thrust into V naught m dot f delta SC. So, you can get very easily, substitute these values and get, that is 46.97, and you can find out the kind of thermal efficiency very easily, and you can note that the I have already discussed about the propeller thrust is quite high when compared to this, TSF is quite small when compared to other engines. So, with this we will stop over here, and in the next lecture we will be looking at real cycle analysis.